Welcome back to our biomass class, where we're delving deeper into the fascinating world of conversion of biomass resources into heat and power. This video was made with the support of Energy. Remember that this biomass energy course has 9 lessons. Lesson 6 has an introduction and several videos that go deeper in some applications of biomass gasification. Let's start with the introduction to biomass gasification. Lignocellulosic materials can be converted into energy by thermochemical processes, which are combustion, gasification, and pyrolysis. The differences between them are the amount of oxygen, which determines the degree of oxidation of biomass, and the products obtained in each process. Let's focus on gasification and particularly in the gasification of wood. As an example of lignocellulosic biofuel, gasification takes place when there is not enough oxygen to have a complete oxidation, and the products are synthesis gas and ash. Let's study in detail how the complex structure of wood can be converted into a fuel gas or synthesis gas. Let's start studying the stages of gasification. Like in combustion, the first stage of gasification is drying. When wood is heated, it dries until all the water is vaporized. The second stage is the thermal decomposition. At 150 degrees Celsius, wood begins to break down. Some of the chemical bonds break. As a result, different chemical compounds are released into the vapor phase. This stage is called pyrolysis and takes place at up to 550 degrees. The products after pyrolysis are charcoal, volatile compounds, and gases. Gasification. When these vapors and charcoal mix at high temperature with the oxygen, they react to produce the synthesis gas. This happens between 850 and 1100 degrees. The partial combustion of part of these compounds release the heat needed to sustain the gasification process. Therefore, compounds like carbon monoxide and hydrogen can be produced. After gasification, the mineral matter remains in the solid state as ash. Equivalence ratio. What is the amount of oxygen needed to provide energy, and, at the same time, avoiding the complete combustion of biomass? The equivalence ratio is an important gasifier design parameter. It is the ratio of the actual air used for gasification to the air needed for a complete combustion. For a good gasification, it must be between 0.3 and 0.35. Values below 0.2 result in several problems, including incomplete gasification. Values above 0.4 results in excessive formation of products of CO2 and water. But let's see which gases are formed. Gasification reactions. After the wood pyrolysis, there are gases, a solid char and water. The complete oxidation of carbon gives carbon dioxide. This provides the heat needed for keeping a high temperature in the gasifier. Carbon monoxide can be formed for the incomplete oxidation of carbon. The reaction of carbon with carbon dioxide gives more carbon monoxide. The reaction of carbon with water gives more carbon monoxide and hydrogen. The shift reaction is the reaction of carbon monoxide with water. This gives carbon dioxide plus hydrogen. Therefore, the presence of water influences strongly the formation of hydrogen. Methanization. Methane can be produced in 2 different ways. First, by the reaction of carbon with hydrogen. And second, by the methanization reaction, which is the reaction of carbon monoxide with hydrogen. A little percentage of methane can increase significantly the heating value of the syngas. Let's summarize the set of reactions. Gasification reactions refer to the combination of carbon and charcoal with different gases. The shift reaction produces more hydrogen, and the methanization reaction more methane. Syngas composition. The main components of a syngas should be carbon monoxide and hydrogen, because they can be burned to produce heat. Methane can also be present. But these gases are not alone. Because the partial combustion of wood, carbon dioxide and water are also present. In an air-blown gasifier, nitrogen goes in with the atmospheric air. Nitrogen dilutes the synthesis gas, decreasing its calorific value. The syngas can also have solid particles, like unburned material, and other pollutants. Tar is a complex mixture of condensable hydrocarbons. Tars are present in the syngas because the incomplete transformation of cellulose and lignin into light gases. They must be removed before sending the gas to a gas engine of an internal combustion engine. Other pollutants. The presence of nitrogen, sulfur, and chlorine in the fuel can promote the formation of gases like ammonia, hydrogen sulfide, and hydrochloric acid, which also must be removed from the syngas. In summary, the raw syngas contains some fuel gases, but also some inert gases that decrease its heating value, and some pollutants that must be removed. Let's see now how is the energy conversion. Energy conversion. The conversion of a solid fuel into a gaseous fuel provides flexibility. The syngas can be used in a gas turbine or an internal combustion engine. However, is this conversion worthwhile from the energy perspective? To evaluate this conversion, the concept of gasification efficiency can be used. Gasification efficiency is the ratio syngas energy to biomass energy, both at standard temperature. That is the efficiency for the conversion of chemical energy only. Depending on type and design of the gasifier as well as on the characteristics of the fuel, it may vary between 60 and 75%. Not so high. For reaching better energy efficiencies, the heat of syngas at the gasifier outlet must be recovered. Wrapping up. Gasification is the thermochemical process that allows converting solid biomass into a fuel gas or synthesis gas. The stages of gasification are drying, pyrolysis, and partial oxidation or gasification. Gasification is done by feeding only between 30% and 35% of the oxygen needed to a complete oxidation or combustion. Gasification reactions are complex and involve the reaction between carbon and gases. Methanization provides some methane in the syngas. The heating value of the synthesis gas depends on the content of carbon monoxide, hydrogen, and some light hydrocarbons. However, these gases are diluted by the carbon monoxide, water, and nitrogen. Impurities like solid particles, tars, ammonia, and acid gases must be removed before using the syngas. The energy conversion is evaluated by the gasification efficiency, which can range between 60 and 75%. Please watch the videos about biomass gasification applications to know more about how biomass can be used to produce electricity. Also, the videos about combustion and pyrolysis to know more about other thermochemical processes.